we can jump into the discussion session. So anyone, if you have questions, you can raise your hand. I can see and you can ask questions.
Troy, do you want to start with yours for John? Also, sorry for background noise.
Oh yeah, sure. So John, I have two questions for you, so I can ask one first. Do you think the real lunar regoliths will make any difference in comparison to the simulants or analogs used in your experiments?
Surely. So it depends not only on the macroscopic, I would say, size of the grain, but also by microporosity, so at the molecular scale. So clearly, the water can be trapped inside these mesopores or nanopores inside the real regolith, and can be released at different temperatures. So also the interaction between so the physical interaction between chemical physical interaction between the water with this structure can be really different. So surely, so it's really important to have the real regolith. So we are just working in that respect in order to have a real sample to be used in this experiment.
Great, thank you.
And the second question I see for the publication, so we are just working all together to have a publication. Yes, so the answer is yes. So it will come in the next month.
That would be fabulous. Can't wait.
Great. Anyone has questions for our speakers in this session?
Yeah, so I had a question for John, the nice talk on TPD. So there was a curious shift for the ice peak to lower temperatures when you had the grains. So I wonder if the grains are hydrophobic, which would give you a lower temperature. And then the width could also be correlated with a different binding energy distribution of defect sites as well as diffusion. So diffusion for sure is important, but the binding site distribution may matter.
Yeah, concerning the second part of your question, so I know your work, and so concerning this respect, so the fact that we have this second bump, the second peak at higher temperature. So I think you are right. So it could be due to the fact that there are different active sites in the sample that can trap the water. But in any case, so I think that the fact that this second bump is just one band, how can I say, so just one bump, not many of these. So it's mostly, to me, related to the diffusion of water instead to the fact that there is other active sites, because in general for minerals the active sites are few, so it's not really a lot. So in this case I would expect to see many bumps, each of them correlated for each different band energy. Concerning the first part of the question, so I think the main is not just the fact that this is hydrophobic, the dust. So it's probably due to the fact that the binding energy and the process of absorption in the case of nickel plated cold finger is different. So the energy is just higher than the dust grains. So this is what we interpreted the result. So the main reason, not really depending on the fact that that is hydrophobic.
Great, thank you, John. I saw a comment from Parvati. She's asking, like, since we've done a lot of work about lunar materials, lunar-like materials across the world, so she's asking, is there a database that compiles all the results, like in previous experiments? I saw Michael has comments. He said right now it's still pretty small. Anyone knows there's such a database?
I haven't heard of a database, but that'd be great. I also think there's probably a lot of research into like desorption for different materials, not in like a planetary context, but like in an industrial context. I've delved a little bit into literature like that, doing my own research, and it can be quite helpful. So finding a database where, information like that would be fabulous.
Yeah, totally agree. I know Tom Armando has done a lot of work using lunar materials or simulants. Not sure he has a database.
I wouldn't call it a database, but we have a lot of data, and we have done data or measurements on real lunar material. And to answer your question, it does look pretty well. The correlation with the simulants, TPD from simulants and TPD with real material looks pretty good, providing you use the material from Dan Britt. If I use JSC1A, that's not true. So it really depends on your simulant.
Okay.
In our case, it's also the same simulant for Britt. So yeah.
Yeah, John, I'll send you this data so you can see it. It's actually a pretty good correlation.
Okay.
Yeah.
Okay, great.
Yeah.
Who do you talk to if you're like, NASA, we need a database? Who does that? The PDS? I don't know.
That was actually a question asked at a recent spectral meeting as well. So I think that's a to be determined question.
I'm glad I'm not the only one with that
So
on
Michael,
my mind.
Yeah, there are a lot of like spectral database regarding like a visible to like even far infrared.
Right, but they're spread out around the world,
Yes.
around a bunch of different websites. There's no like PDS equivalent where you just go to one node for everything you need.
Yeah, I know Relab is joining PDS, so they are developing a portal. You can search what you want.
That is actually exactly what brought this into my mind, was Relab's recent transition into the PDS and just how useful that has been. And like wondering, because I know that there are PDS nodes for missions and instruments, et cetera. But if, there were also like important quantities that could be collected from various studies and put in one place, that would be like a fabulous PDS resource. But I don't know if that's how PDS like funding works.
There are some comments in the chat regarding PDART.
Yeah, I think that's pretty clearly within the purview of the PDART program. So whatever that stands for, Planetary Data Archiving and Research Tools.
Remember that acronym.
This is Alex. Just a quick note. It just came across my desk recently. There's a new database that's being built. It's called Astromat. It's all kinds of, it should focus on lunar stuff, but probably more than that. So maybe that will be one in the future we can go to and people submit. We can pull out all the data from there. So potentially.
That's great. Thank you for sharing the link, Alex.
Ooh.
Any further questions? Can I? Okay, I'm the chair. Okay, I can. So Paul Hein, I have another question to ask. Is it possible to use ARIS to discriminate like a buried ice from like buried rocks?
Oh, wow. I think if we had like a year-long mission, maybe, but with the short, 14-day duration on the surface, during sunlight hours, I don't think we'd be able to discriminate between buried ice and buried rocks. Especially because I think the temperature response at the surface would be very similar, given the uncertainties we have in the configuration of the ice and its density.
Okay. Well, hopefully your mission can last longer.
Yeah, I'm hopeful that in the future, we can deploy radiometers like this for much longer missions.
Mm-hmm.
And Matt Sigler and his group have been doing a lot of good work looking at the use of longer wavelengths or lower frequency measurements in the microwave range to look directly at the both the thermophysical and dielectric properties in the subsurface. And so that's another sort of independent technique to sense in the subsurface.
Is there anything new on the microwave stuff? Do you know, Paul? Because I remember seeing it at LPSC a couple of years ago, and it was mind-blowing a little bit. But I don't know, with the pandemic and everything, I've kind of lost track of what's going on there.
Yeah, I would suggest starting with the papers from Fong. It's F-E-N-G, Jianqing Fong. So he does. He's been working with the MWR data from the Chang'e orbiters, and just sort of branching out from there. There's been numerous publications from that data set in the last couple of years.
Awesome.
Paul Lucy had asked a question to both Shuai and Miriam, and I just wanted to give Miriam the chance to also answer if she wanted to. But Paul had made a comment about how ice regolith grains would be very short-lived. And of course, ice cobbles would persist much longer. And just asking Miriam if you had anything else you wanted to comment in addition to Shuai's response.
Yes, thank you. Well, we're really looking forward to be able to analyze the variation in time that we can potentially see with the SP data through the about 1.5 to 2 years of acquisition. So yes, we're certainly going to be looking at specific places. If we can see changes in time, then we'll look in that direction. Yeah.
So Ariel, I have a question for you. What kind of like a resolution when you say like roughness? The moon and the Mercury, are they, the same scale resolution, or it's different regarding to the roughness?
What I presented today was almost similar resolution. So 120 meter for the moon and 125 meter for Mercury. The coarser resolution, sort of like those larger scale variations you're seeing. So the results are like hectometer scale roughness. Yeah. If the DEMs are different scales, it doesn't really make it, you can't compare because you're looking at different topography variations.
Okay, thank you.
I was also just going to add, Shuai, another thing is like, even with higher resolution DEMs are available for the moon. Theirs are based on higher amounts of interpolation. And so being able to look at the roughness at the 120 meter scale allows for these measurements to be made on actual LOLA pulses, which also is important for this measurement. And I think Elizabeth has a comment, and then also Paul Hain put in some paper links for the microwave data in the chat. So thanks, Paul.
Yeah, Elizabeth, do you have a question?
Ooh, yes. Well, it's like kind of a very specific question, following up on the one I asked you earlier. I'm super curious about looking at those plots again, where you were looking at the 2 micron band depth versus the ice abundance. And remind me, was that like physical ice mixed with regolith, or did you mix water in, or?
Yeah, it's physical ice sieved into 63 to 75 micron, mixed with analog, a marble glass, and also at the same particle size range. So the mean particle size is around 70 micron. So physically mix them together independently and then measure the spectral at a standard viewing geometry, 30-degree incidence, 0 impedance, and a 30-degree phase angle. And also you can see I did a simulation using the radiative transfer model to mix ice with the different Apollo samples and also the analog. It's very interesting to me. Is like the whole trend won't show any like a compositional dependence, and also won't show any like a maturity dependence, because Apollo 11 is more mature than Apollo 16 samples, so they all follow on the same trend.
Yeah, I mean, that's what I'm really curious about, because obviously that's a good place to start with ice particles and, you know, regolith particles that are a similar size. But I had noticed kind of towards the lower end of your graph, if that, I can't remember if that was lower band depth and lower abundance, your trends kind of started to deviate in an interesting way, to me at least. They didn't just scatter, they seemed like they were kind of following some sort of trend.
Yeah, you're absolutely right. Yeah.
Yeah,
that's because the absorption of the host mineral, host regolith. Yeah, you're right. But the different, you know, the deviation is kind of small in comparison to the whole trend, the scattering of the whole trend.
Yeah. Oh, wait. So what exactly was causing the deviation at the low end of the graph?
So the Apollo 16 sample and also the marble glass I used show a 2 micron absorption feature. So it's kind of like overlapped with the water ice absorption. That will, you know, because the 2 options overlap on each other, you can overestimate the absorption depth. So that's give you the deviation. But, you know, we know on the lunar surface, the 2 micron absorption are typically much weaker than the 1 micron, and most of them are featureless. So yeah, even though it has effects, but the effects is small.
Yeah. So I wonder, with like the lack of the compositional dependence, do you think that could be related to the fact that the ice is either it's just brighter or more transparent to a degree where you're just over printing the variations from like the much darker, like overall darker regolith entirely? I'm assuming that both the samples you used, like they were both lunar, correct?
Yeah, I think you're right. Maybe because the ice absorption is much stronger. It's very strong absorber, right? In the IR, in IR region. So and also the environments I use, the regoliths I use are normally featureless in 2 micron. I think that's the reason why we don't see a compositional dependence. So I'm going to use like some maybe pyroxene samples to see. I would imagine it will show a strong deviation.
Yeah, that's super interesting stuff. And I mean, I don't want to monopolize the conversation here, but I'm curious to see what will happen when you start varying the particle sizes a little bit more and have different particle sizes of like ice and like regolith, for example.
Yeah,
yeah,
we're doing the work now.
Cool stuff,
Thank you.
dude.
Thanks.
Thanks, Elizabeth. Those are good questions. There's also one more for Shwai and Miriam from Parvati in the chat, asking if you've thought about using N-Cube and Kaguya SP data to look for non-water volatiles.
Not yet for SP. That was really a first preliminary look, and I was really surprised to see how good the data looks. So it's something that we can definitely do in the future.
Yeah, so that's really good question. So I talked to, I discussed with Norbert a long time ago, since he's doing the work to map the carbon dioxide region in the lunar PSRs. So when I saw his map, I feel like, oh, the region is too small to average enough MQ pixels to reduce the noise to see the real features. In addition, the CO2 feature in the visible to, particularly in the IR region, is too sharp. So normally, I think less than 20 nanometer or less than 40 nanometer. Oh, well, that's the spectral resolution of MQ data. So the spectral resolution of MQ data may not be sufficient to discriminate like a CO2 at least. Yeah, we need more data, particularly for PSRs. That's a big gap currently, I feel. Fortunately, we will have more and more mission to the polar region. So Ariel, Paul has a question for you.
Sorry, it's super loud here, so I'm going to respond in the chat.
Where are you?
I saw it.
I mean, if there aren't any more questions right now, maybe Ariel could regale us with the latest and greatest on Viper, the drama of the mission.
I would love to hear.
Yeah.
Oh.
Ooh.
So like, what instruments are you most excited, this is a question area, to see developed to the surface of the moon this decade?
Yep, sorry, it's a little quieter. Parvati and Caroline suggested we put together a poll so you can go to this website and hopefully type in the code and answer. Hopefully this works and it should update real time.
So is this an instrument that's in the pipeline or whatever instrument we can imagine?
Whatever you want. It's just for fun and to get a pulse of people's thoughts.
I feel like I'm biased because I want to send my own one to the moon. So
I'll vote for humans.
I'll vote against humans too soon.
Why?
Humans are really, really gassy and take bigger spacecraft. I want to see it as it is before we see it as humans have turned it into.
And poorly designed machines that degrade over time.
I feel like we could have a whole discussion about whether humans are poorly designed or like incredibly designed.
I'm just joking because I'm feeling I'm aging and I can't reverse it.
Oh no. I was thinking along the lines of like, you can remove a kidney from a human and the human is still functional. I'm trying to think of a robot where you can just pull a part out of it and it's like, nah, I'm good.
There's plenty of stuff designed with redundancy.
Okay, well, I don't see any other questions in the chat. But yeah, I think we should thank everyone that contributed today, and also a huge thanks to Ricky and everyone for technical support. I'm sorry, it's so loud here. I'm gonna mute.
Yeah, I think yeah, we want to thank everyone for participating in this session. We definitely had a great time, great talks, and also we want to thank Ricky for the technician work, make the session went so smoothly. And if we don't have any further questions, comments, I think we can end this session and let our European folks to have a good sleep. And both me and Ari, we are located in Hawaii, so we got up at like 4 o'clock in the morning. Yeah, so I also need a rest.
Time for bed, man.
Yeah.
Enjoy.
Thank you. Okay, so see you everyone. Thank you again.
Thank you.